Nathan Kabza. I'll be presenting on behalf of the FlappingMAV Micro Air Vehicle team. Our team leads couldn't be here today, but we have Sam, Tristan, and Wade. So a little bit about FlappingMAV Micro Air Vehicle. We are an undergraduate and graduate research team under Professor Haitham Taha. And this was started through Professor Taha's research on the stability, maneuverability, and agility of flapping wing systems. So Professor Taha was inspired by the incredible agility and stability of a hummingbird, and in a lab setting, he was able to recreate it with a grad student in a 2 degree of freedom pendulum test. And this was using an ornithopter design, which is just a standard, it's a mechanical set of flapping wings. But this opened the door to a lot of other research possibilities. So this mainly focuses on unconventional lift generation. So where conventional lift generation would be a fixed or rotary wing, unconventional lift generation would be more like insects or birds, which use nonlinear aerodynamics, time-varying dynamics, and unsteady systems to generate superior lift and agility. So recent advancements in mathematics has kind of opened the door for this field. There's a lot of complex systems involved with this. So before, computing power wasn't really there to solve these really advanced systems. So in recent years, this has kind of been an exploding field. And with these unconventional lift systems, we want to compare the possibility of flapping wings being better or preferable to fixed or rotary wings. So this leads us to our research goal, which is to explore these advantages in flapping wings over fixed and rotary wings for small-scale applications. So this leads to our different teams. We have the quad flapper team, the mechanism team, and the system identification and visualization team. The quad flapper team, the quad flapper team is a flapping wing UAV. It has 4 pairs of ornithopters attached in a quadcopter formation. And this is mainly so that we have a working demonstration of flapping wing ability so we can do comparison testing with rotary wings. So we built a quad flapper and a quadcopter so that we could accurately compare the 2 systems. And then the mechanism team is trying to create advantages in our existing ornithopter mechanism. So they're modifying, augmenting these existing mechanisms so that they better mimic the motion of a hummingbird, so we get more lift and better efficiency. And then the system identification and visualization team is highly research-based, so they're focused on getting these flow fields around the wings and mapping these systems of equations so that we can better understand them and improve on them. So our milestones for winter. Last quarter we completed and did comparison testing between a quadcopter and a quad flapper, and we presented that at an AIAA conference in January. And so this quarter we're going to be doing the same exact comparison testing except in smaller micro air vehicle applications. So a micro air vehicle is something less than 15 centimeters in any principal direction. So the quad flapper team is going to be attempting to do the same sort of comparison testing, but in a much smaller scale. The mechanical design team is trying to manufacture an active pitching mechanism. So this mechanism is suited for mimicking the motion of a hummingbird. The active pitching just means that the wings tilt dynamically and throughout the stroke angle of the flap. And then the simulation and visualization or system identification, they are trying to construct a flow visualization rig for particle image velocimetry. So using a laser, you can shine it through a collimator lens and get a single plane flow field around the flapping wings. And using MATLAB and advanced processing, we can get the pressure differentials and all of the very, very complicated flow around it. So our timeline. So for this quarter, our most important milestones are to complete the active pitching mechanism, to complete our tuned comparison, or to complete both the micro air vehicles, the quad flapper and the quadcopter, like the small scale ones, and then to finish construction of our flow visualization area. And those are all to be done week 9 or 10. And so progress so far. So our quad flapper team has finished construction of these were taken from videos, so it's a little bit blurry, but they finished construction of the micro air vehicle quad flapper and then the small scale quadcopter. So remaining is tuning and testing for these two UAVs because they're still slightly unstable right now. The mechanical design team has completed a preliminary active pitching system. So this is an unoptimized but working active pitching mechanism. So they designed it, they calculated the gear ratios, and they achieved a 30 to 40 degree stroke angle of the wings, but ideally we're looking for over 80 degrees for each wing. And then the simulation and visualization team, they finished the design and purchasing of all of the necessary parts for the flow visualization rig, but they still need assembly and safety training and safety equipment for class 4 lasers, which can damage your eyes and skin. So the design requirements for each sub-team, they're all different. The quad flapper team, the namesake of the flapping wing micro air vehicle is that it's a micro air vehicle, and micro air vehicle just means that it's less than 15 centimeters in any principal direction. For the quad flapper team, they have to do comparison testing, so we have to make sure that our systems are actually comparable. So to do that, we have to use the same actuators, flight controller, battery, transmitter, receiver, flight controller software, and try to get an approximate center of gravity and moment of inertia. And then for tuning was a difficult choice between optimizing both the quad flapper and the quadcopter for their peak performance, or to try to keep the gains in the PID tuning to constant levels so that we could just be comparing at a baseline. But we ended up going with tuning for the peak performing system for each quad flapper and quadcopter. And then the mechanism team, the term active and dynamic pitching, there has to be a set phase shift between the upper and lower cranks. So the mechanism involved is it's a crank rocker mechanism driven by a brushed motor. So there's an upper carrier and lower carrier mechanism. So there's two different rocker sets. So that just means that the upper rocker is going to be slightly out of phase with the lower rocker so that the wings can pitch throughout the stroke. And this mechanism must withstand high frequency flapping, so greater than 20 hertz, as observed with the Hummingbird. And the materials have to be light, so ideally for the single set of flapping wings, we want the lift to be greater than the weight. So we can't use metal for our gears, so it would be preferable so that we would be shredding. The system identification visualization team, so they have to be very careful with these lasers. So that's their primary concern this quarter, is setting up the necessary safety precautions so that they're eligible. And they have to design the rig in such a way that you can adjust the smoke volume, the quantity, and the direction. And our laser and collimator lens must be adjustable too. So that's in 2 degrees of freedom. So engineering principles employed. The quad flapper team, very strict tolerances are needed. We had to calculate the moment of inertia for each the quad flapper and the quadcopter so that we could accurately compare them. The shape of the components too, we had to make a very tough choice between square tube carbon fiber rods or circular tube carbon fiber rods. We ended up going with circular. We had to use feedback and control loops for the PID tuning, power voltage and current. Those are important considerations. So those directly affect flight time based on battery and modal analysis. So at certain frequencies, the quad flapper tends to vibrate. So to avoid resonance, we had to make sure that the resonance frequency of the drone was either well below or well above the operating frequency. The mechanism team also uses tolerances, yield strength, shear torque. The S&D team uses waves and optics, power voltage and current. So funding, we have historically always had an underutilization of our budget. Each team is allocated $600 per quarter, and the remaining funds will end up going to lab supplies. So future applications of the drone. So the quad flapper is already a highly viable product. We made a business case for it last year. And as it stands, the quad flapper could be sold as like a toy or yeah, just a very entertaining drone. But it's much safer, more agile, and has lower frequency sound generation than a standard quadcopter. But we see future applications for like reconnaissance UAVs, consumer drones, non-invasive data acquisition drones. And then there's also the potential to operate a hybrid. So if we were to tune down or shut off 2 of the flapping wings, we would still generate enough upwards lift to sustain the weight of the drone. So we've observed that in our ability to sustain very high angles of attack for the quad flapper, which the quadcopter is unable to do. And in general, the outcome of the project that we hope to achieve is to inspire more flapping wing propulsion systems. So we want to see new technologies and drive future innovation that are related to flapping wings because this is a very interesting and unexplored field. So that's all.